Okay, so for those that are on Zoom or looking at this video, I've given you the alternative to do DryLab 10 as a acid base worksheet. If you go to Unit 2, it's called Alternate DryLab 10 Acid Base. Okay, so let's talk about free energy. Now, there are three variables in free energy. It is potential energy, which is called enthalpy, and I'll write all this down, entropy, and temperature. I want to talk about temperature first. So temperature we're working in thermodynamics now. Whenever we work in thermodynamics with either free energy or gas laws, we have to work in absolute temperature, not relative temperature. Now, this is what I mean by that. Okay, the relative temperature is basically what you're used to using, either Fahrenheit or Celsius. That would be F or C. And it's arbitrary. What I mean by that, it's based on two things. Based on freezing point of water and the boiling point of water. Now, we've already talked about all molecules move in various different ways. And this would be 0 and 100 or 32 and 212. What happens when we slow things down to the point where there's no motion? Because motion is, the metric for motion is kinetic energy, 1/2 mv squared. And at freezing of water, there's motion. Even though solid ice doesn't look like it's moving much, it's definitely moving. Boiling water, same thing. So if we use the absolute scale, which is based on no movement at all, that's called Kelvin. Kelvin goes down, 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 down to the point where there's no molecular movement at all. So that is absolute zero. Which is minus 273 C.
395.
5065.
And then the
Are we still on?
To get an
Yeah.
absolute zero, it takes a horrendous amount of energy to do that. Okay, so all the considerations under free energy and gas.
The doctor put that prices on there earlier. Was
So
they?
that is C plus 273.
This is a different
Okay.
type of Roseville. I had to go there earlier to see the
The K
doctor,
is always
but I
the
had
bigger
already
one.
hot.
So if you're trying to convert between the two,
He said,
what are you starting with? Starting with
I
C?
mean, but I didn't know.
Or are you starting with the
He's showing
K?
up there. What? No.
It's not
Like.
And if we were talking about Fahrenheit, it's called Renkin. Same idea.
It would have been Dr.
Renkin,
Cagden.
Zero.
If he did,
Everything is
Five.
no movement at all.
so ornament of that.
Okay, that's the first thing I want to talk about. is
But otherwise,
temperature.
I'll just pick up the other
Because
one.
temperature determines a number of things in terms of spontaneity of a reaction.
Don't see anything yet.
Hotter
Okay, it
is
would have been
the
in there
more
because he called in another
tendency
medicine I picked up. I
to
just
become
totally
spontaneous.
dropped, get my
So-
mind earlier when I pick up the medicine. He asks about the best situation.
Temperature
Maybe
is directly related to
I could, I don't know. Something.
Sometimes it's just the counter, so
So maybe he
it
didn't.
would be,
Well,
it wouldn't be here.
T. I think I
oh,
spelled
because
it
he
wrong.
did say,
Tom,
I mean, if you either one. So I thought maybe that was
Oh,
like
well,
a
phonetically I
part
spelled
one,
it wrong.
so I don't.
Okay, that means if the temperature goes up, there's a more likelihood the reaction will go. Lowering the temperature, the likelihood of the reaction going will be decreased. Okay, does that make sense? T goes
They
up,
did.
spontaneity goes up. And we're gonna see this in the gas laws. We're gonna have certain things that are indirectly related. When one goes up, the other goes down. And also when one goes up, the other goes up. Okay, so spontaneity.
But it's just an over the
Directly
counter. I
related.
can grab it for you. Amazing.
Another one is potential energy.
I have refilled also
The fancy word for potential energy is enthalpy. And that is H. And usually it's not H, it's delta H. So direct related again. Actually, excuse me, it's indirectly related. So as delta H goes up, the spontaneity goes down.
Hello.
Okay, the last term is entropy. And that's delta S. Okay, entropy is directly related to spontaneity.
Thank you. And Stan.
Okay, so mathematically,
This
this is what these guys look like. So we're looking at delta G, Gibbs free energy, is equal to delta H minus the temperature times the entropy. Now,
If we have like one of those.
delta G is inversely related to spontaneity.
I'm gonna ask you to strike your toes, but
The last two, potential energy, just briefly.
On which one? This one here?
Yeah. You said it's reversed, so if potential H goes up, then it will decrease. Okay, I just want to,
You just think,
it will likely will happen, the reaction will occur.
Yeah. So with increased enthalpy, the reaction will not occur.
Will not.
Okay, increased entropy, it will.
You guys normally put that.
Okay, so this is the mathematical relationship here. Now, if delta G is less than 0,
I have anything.
it's spontaneous. Okay,
Yeah, that line in the middle.
so we've got two operations going on here. We've got We've got enthalpy versus temperature entropy. Which one is greater, basically? So this is why increasing the temperature makes it more negative. That's why it's more spontaneous with higher temperature. Also, delta S, the entropy, if we can increase the entropy, it's also more negative. With H, we increase that, the delta G becomes more positive, meaning that spontaneity is not going to happen as readily. It can still happen, but just not as spontaneous. Now, in your dry lab today, they're going to ask you a whole bunch of questions about, is spontaneity favored or enthalpy? And I gave you the answers because I'm not sure it's all that intuitive, especially when you're just starting out. So I gave you all the answers. Now you can actually, if you were taking 400 or 401, you have to do a whole bunch of these calculations, a whole bunch. And at the back of your book is all the delta S and delta H values for various chemicals. And you have to put those together to figure out whether the reaction is going to go or not thermodynamically. And we're talking about thermodynamics now. There's two factors whether a reaction will go: thermodynamics and kinetics. Okay, so let's talk about diamonds and charcoal. Remember we talked about that? Which is more stable, charcoal or the diamonds? Charcoal is more stable. Then why doesn't the charcoal turn into diamonds? Because thermodynamically it's favored, but it doesn't happen in real time. One.
Not a P. Was it not a P applied like continuously at one time?
The speed is very slow. Remember kinetics, speed. So we've got speed versus thermodynamics. Okay, so in the case of the charcoal and diamond, through the delta G formula I just gave you, charcoal is favored. It's got a negative G value. However, when it converts from diamonds to charcoal, it does it so extremely slowly, you don't even know what's happening. So your investment doesn't convert to worthless charcoal. Now, there's a couple things you can do thermodynamically to change that. The easiest one is this: temperature. If you jack the temperature up to 1,000,000 degrees or so, the reactions become more negative. The more negative, the more spontaneous, the more spontaneity is favored. But you got to jack the temperature up really high. Really high.
So when does that occur? Is it like? Can you give an example of when that would occur, like when it has occurred in our time or like a period of
Yeah,
time?
that's how they make industrial diamonds. There's a giant press. I mean, giant. You put your little charcoal there, and it comes down and
I thought
crushes
they
it
made that, oh, is that what they need?
with intense pressure, which jacks up the temperature. Industrial diamonds are made all the time.
Perfect.
Yeah,
So delta H and delta G are inversely related to spontaneity.
yeah, so delta H is inversely related to whether the reaction is gonna happen, spontaneity.
Delta S is directly related, and so it's
Delta S is entropy, H is enthalpy.
Okay. And they affect each other's relationship to spontaneity.
Yeah, if you go back to this, equation right here. Entropy temperature is on the right.
Yeah.
And it's negative. And we want delta G to be negative if the reaction is gonna go or not. So that's why increasing entropy or temperature will make the reaction go. Let's say that you put the stuff together, nothing happens. Okay, that means delta G is positive.
Yeah.
So nothing's happening, right?
Yeah.
Okay. Heat it up.
Changes the relationship to the
Yeah,
spontaneity.
as long as you get over the delta H by heating it, the reaction is gonna go.
So when in doubt, just change the temperature and it'll change the
And
relationship.
it's hard to increase entropy, but it's easy to increase temperature. So that's the big variable.
Mhm.
And it's Kelvin degrees. Okay, now your book, or not your book, your lab gives you some examples like for enthalpy. What does hot toast do? It doesn't get hotter, it gets colder. So the reaction is getting colder, not hotter. The entropy, ice melted. Ice goes from a solid to a liquid. Solid's more dense, more organized, liquid's more random. So the entropy, the randomness factor is greater with liquid versus solid. So delta S is going to be favored there. Anyway, your lab gives you some examples and they don't give you they do 2 calculations instead of 20. And it doesn't give you any practice at all. So what I decided to do again is give you an alternate lab for today and tomorrow. That's where you practice acids and bases, which is very fundamental to Unit 2. Okay? All right. And you can find that under Files, Unit 2. It's at the very top, and it says alternate lab 10. Okay, are there any questions about that? In 400 and 401, it's emphasized. And here it's de-emphasized. Okay, so let's go on now. And what I want to start is your next week is going to be gases, dry labs. You have 2 dry labs for gases. So I want to talk about the ideal gas law. Okay, so we've got okay, that's the ideal gas law. Remember we talked about gases at standard temperature pressure is 22.4 liters. That's only at STP. What if it's not at STP? This will tell you what the liters will be. Okay, so P is in atmospheres. And there's a lot of ways you can use pressure. There's millimeters of mercury, atmospheres, torrs, there's a lot of, and in this class, we're using atmospheres. It's the simplest and it works. Okay? That's your gaseous volume in liters. N is number of moles. T is temperature in Kelvin. And R is the gas constant. And the gas constant varies depending on what units you use for PV and mainly for PV. Okay, and this class is going to be and there's a whole bunch of units there, so everything cancels out. And let me verify if I remembered correctly.
These are great. It's like, what just. You didn't.
So I've seen that. That's something. If you just. When you're paying down or pH. Different way Yes.
This one's the one that you're right. This one.
Yeah.
You have to,
Was it 0831.
You have the Muslims.
Okay.
Is it going to
With one of these,
the gas constant?
what's the?
Is it you said 0831, but you wrote 0832?
Yeah, but if you round.
Oh, you.
Okay, so let's do a problem. Okay, what's the volume of a balloon with the following parameters? 2.3 atmospheres, 23.4 degrees C, and 2 moles, and that's 2.00. Moles of the gas. Okay, so we're looking at PV is equal to nRT. Okay, let's solve for volume. So volume is equal to nRT over P. Okay, our number of moles is 2.0. R is 0832. And temperature is 23.4 plus 273.
Oh, that's Kelvin. 273.
273. Hey, did everyone see or got the numbers?
Just added to 30 and 20. Since yes, Los Angeles, what the yeah. For the United States, if the basement is
My sharp students.
you have to contact. We do need to.
Okay. Okay, so the size of that balloon is going to be 21.4 liters. Now, there's two situations I want to talk about in terms of gas laws. What happens when you just want to know the volume or pressure of something? You use the PV is equal to nRT. What happens when temperature parameter or when parameters in general change? You've got initial parameters, final parameters. What are the new conditions? And then how does that affect pressure, volume, number of moles, and temperature? So that's the second set of scenarios. Okay, are there any questions about where I got the numbers?
Did you just add 230 and 234?
How do I get what? The 273?
So I see that you got 230.4 from the problem. Well, yeah, but how'd you end up with 273?
That's the Kelvin.
That's how
The negative 273, the Kelvin unit of the freezing point.
Yeah, if you're given centigrade to convert to Kelvin, you have to add 273. If you're given Kelvin, and you want to know Kelvin, then you subtract 273. Okay, so this is a typical problem. Frequently, they're given changing conditions. In other words, we have a balloon on the top of Mount Everest, certain size. Then we take it down to sea level. How did that change? Now it's a sealed balloon. How do we do that? Okay. So let's do one more problem using the straight ideal gas law. And by the way, we're not going to go into this, but when you're looking at stoichiometry with gases, you got to use the ideal gas law up front to get moles. If you solve for N here, N is equal to PV over RT. And that's what you place instead of the molar mass. Because you got to get to moles in step one in stoichiometry. That's how you do it, using the ideal gas law. Now, the reason why it's called ideal, by the way, that's under normal conditions. Under heavy duty pressure, like a couple hundred atmospheres, or extremely high temperature, like in a plasma situation, you have to modify the ideal gas law. And that's what you do in 400 and 401. But normally you use the ideal gas law for most things, because we're not sitting at hundreds of atmospheres pressure, unless you go to, I'm not sure if Saturn's atmosphere is that harsh. Jupiter and Saturn's climates are they're extremely cold and they're very harsh. Okay, so let's do another one of these.
Can you repeat back when you said when we add the Kelvin unit up to 73, when we're trying to find the volume? Or you said when we subtract the 273
That when you subtract, you go from Kelvin to C.
to see, oh.
So K is always higher than C. So if you're starting with a lower one, you have to add to get higher. If you're starting with a higher one, you got to subtract to get to the lower one. That's how we're.
Okay.
Does that make sense?
Yes.
Okay, so let's see. Okay. Now there's an assumption. If they don't specify moles, it's always 1 mole. Okay. So non-specified moles is 1. So if I left off the 512, you don't have to worry about it because it's gonna be one. Okay, so PV nRT, we want T, so that's equal to PV over NR. Okay, so pressure is 312. Volume is 423. Number of moles is 512. And N is does everyone see how I came up with T is equal to PV over NR? Yeah,
Isn't the constant 0.32?
I'm sorry, say again?
The constant, isn't it 0.32?
Yes.
It's a great.
Okay, well, it's gonna be kind of hard to subtract 273 from 31, but the way you would theoretically, it would go. So minus 242. That's one cold balloon.
But then you asked us in Celsius, wait, that was in Kelvin, oh, cause it's.
Remember 273? So K is always higher. So to go to Kelvin, or to go to centigrade, you gotta drop the numbers. That means you gotta subtract 273. Question is either add or subtract, which one?
So 30 is the Kelvin.
The 31.0 with that. We have to find the temperatures, which is T, is what we're looking for.
Okay, does that make sense? Now, next week, there's two dry labs or gas labs. I need to review them. It seems like, although up at Sierra, we did two dry labs for kinetic, for gas labs. Okay, so what I want you to do is, go ahead and start the dry labs, either the alternate or the official one, either one.
Alternate.
Yeah, if we go to,
These official stuff that happened where. Who wrote it?
if you go to, Files, Unit 2, alternate dry lab 10. Either one.
Circle?
Listen to me.